Okay, so we'll pick up where we left off last lecture. One thing I want to add, so I'm going back to the earlier slide, and one thing I want to talk about there, remember we had that rule of thumb for clockwise, counterclockwise for work done on or by the system. So after I thought about this some more, I came up with, one of those, I forget I came up with one of those, analogy type processes where you can figure out whether it's for a TS diagram, whether it's heat in or heat out. It's not necessarily as nice as the one with counterclockwise, clockwise, work on, work by, but it still works. And so let's consider this TS diagram. And if I go from state 1 to state 2, of course, state 1, I'm at a given temperature and I'm at a given pressure. Given I know the temperature and pressure, I know the entropy at state 1. So I can go from state 1 to state 2. And let's just say it's a reversible process. So if it's reversible, then I can go back from state 2 back to state 1. And the area under my curve for that cycle represents the heat transfer, right? And so there's no area, there's no heat in, there's no net. So there's net heat in or out is in and out are 0. Now let's say I take a reversible process. So I go from state 1 to state 2, and then I come back, right? Typically, you're always going to have some area under the curve here. And so this represents counterclockwise, right? And so I have some area. Now, what I did is, so counterclockwise, there's 3 letters. Out, so Q, net, out, counterclockwise. So if you have, now this applies to a cycle. Now of course, if it's only from 1 to 2, right, or 2 to 1, it's hard to say necessarily whether it's net heat in or out. But for a cycle, when you come back, the area under the curve represents that. But in general, this usually works. So I'm at a lower temperature, right, I add heat, right, so I'm adding heat to the system, and I'm increasing its temperature, and given that I'm adding heat, typically, and the temperature increases, there's going to be an increase in entropy of my system, right? I added heat, I go to a higher temperature, just based off of the third law, we should know the entropy increases, right? So this doesn't necessarily have to be a process that is natural, right? So this could be, and so this process from going from temperature 1 to temperature 2, I could be doing work, I might not be doing work. I'd have to look at a PV diagram. So I could go from state 1 to state 2 at constant volume. Given that I do that, I would be, and if it was an ideal gas inside, I'd be increasing its temperature and pressure at constant volume, so I'd just be pressurizing my gas and increasing its temperature. And by doing that, I would be increasing its entropy, and there'd be no work done because it would be constant volume, right? Now when I come back, let's say I remove heat from my system. To get back to this temperature and pressure, because there was an increase in entropy, I actually have to remove more heat. So it's harder for me to get back here by just purely removing heat. So if I remove the exact same amount of heat, it's a reversible process, I can get back here. But when it's irreversible, it's hard for me to get back to this initial entropy unless I remove an additional amount of heat. For this process, both of these are constant volume processes. So I have to remove a little bit more heat from my system. So this is a natural type, or the positive, or this area for counterclockwise, net heat outwards. Now, on the converse, if I were to go up and then come back down, realistically I wouldn't be able to do that, removing less heat, unless there was some work in, right? So when it's counterclockwise, or clockwise, right, 2 letters in QNet in clockwise. So I just did 3-letter, 2-letter type, I don't know, It's just one way to remember it, right? And we revisit, the last thing we did is we revisited the TS diagram. Since this one was so involved already, I didn't put the clockwise, counterclockwise on it. But the end point was you go through a cycle, right? State 1 to state 2. Doesn't matter what path I take for my cycle, there and back. Given I'm back at my initial state for a cycle, we know the change in entropy and the change in internal energy is 0 because I'm right back at my initial temperature and pressure. So for a cycle, I have my delta E is equal to 0 and my delta S, and so I can look at this, and so for a reversible cycle, this is equal to 0, right? The area under the curve, so that means I have no net work for the cycle. Okay, so now we're going to introduce some other processes. So we've talked about isothermal, right? Isobaric, polyotropic, adiabatic, different types of processes to go from one state to another. And so now we're going to introduce another type of process, which is called an isentropic process. So an isentropic process is a process that is internally reversible and adiabatic. So a quote-unquote reversible adiabatic process. So if it's reversible, that means we already know that from reversible that there's no net heat in and net heat out. And adiabatic, we also know that delta Q is equal to 0. But when it's both of these, reversible and adiabatic, so reversible, we had no work, but the end story is for isentropic process, delta S is equal to 0. So on a TS diagram, for delta S to equal 0 from one state to the next, right? I start here at state 1, delta S is equal to 0, so I go here to state 2, and I can go back, and you can see that this S1, 2. So on a TS diagram, if I say isentropic, you know that it's a straight line. And of course, there's no area under this straight line curve for the cycle, right? So we know it's net heat in and out. Well, a reversible adiabatic, we already know from adiabatic. So adiabatic doesn't necessarily mean that delta S is equal to 0, but isentropic says it's delta Q is equal to 0 and delta S is equal. So I'll just write again here for our clockwise, counterclockwise, and I can have state 1, state 2, and let's say I have a counterclockwise, and then 3 letters. Net heat out of the system. And for clockwise, so I can go to state 1, no, state 2, and then back. Clockwise, 2 letters in, net heat into the system. So ideally one wants the heat as a function of temperature to calculate delta S, right? If I just go to my tedious question, right? So I can rewrite this, and I can have S equals the integral delta Q over T. So if Q is a function of T, I can calculate delta S. nice way to do it is if I have Q as a function of T, and I know the boundary temperature of my system, I can always calculate the change in entropy by heat. The exact the heat as a function of T, however, is rarely now you can take heat transfer classes and you can use heat transfer models to get the heat, right? To predict the heat. But like if I take the conduction equation for heat transfer, so I have here Q is equal to the thermal conductivity times the temperature gradient. So I have some expression. But the thermal conductivity is a function of temperature, which we really don't know exactly. It's a temperature gradient. And so you can use heat transfer models. They work, but in a lot of cases, it's not precisely known, right? Typically in thermodynamics, one knows, though, S as a function of temperature. And an example of this is a steam table. Okay, so if you look in the back of the book, you can pick a gas, you can pick, you look online, you can go and pick up a handbook on thermal properties of metals, right? And it's going to tabulate what somebody has measured for the entropy at a given temperature and pressure. In the back of the book, it has all this, the entropy tabulated for various gases and liquids as a function of temperature and pressure, right? So this is well known. But I want to get to kind of what I consider the heart of Chapter 7, and this is the whole idea of energy, mass, and entropy balance. So let's draw my system, right? And I can have energy in, I can have entropy in, I can have mass in. Now the idea of entropy in is kind of strange. Really, it's some mass of a given entropy entering my system. So really it's but I could put a big S, which is equal to, right? Or I can have something where entropy N is related to some heat in over some boundary temperature, right? So entropy entering my system has two contributions, heat and mass. Mass is likewise, so I can have mass out, or I can just have in general energy out. And here I can say heat out, heat in, and big S out. So this is my system. Sgen has to be greater than or equal to 0. Now this is the entropy generated within my system for energy coming in and energy leaving. I do have a delta S in my system. So I could have a change in entropy in my system without any entropy generated. Typically, if I have a change in entropy in my system, I'm going to have entropy generated too. So this can be negative, positive, right? So if delta S of the system is negative, typically we had to do some work to accomplish that. But if delta S of the system is negative, even if this is negative, the entropy generated within my system has to be. So it's kind of confusing, but I can do work to decrease the entropy of my system, but that doesn't necessarily mean that the entropy generated is 0. Okay, so let's go to simpler concepts. I have a change in mass in my system and a change in internal energy in my system. Or I could look at this relation between the volume and pressure of my system and get a delta, a change in enthalpy in my system. Right? I'm not going to do an enthalpy balance, but I'll just write out here the energy balance. So I have energy in minus energy out. equals the change in internal energy. Okay, for mass balance, I have mass in minus mass out equals the change in mass of my system. So this represents all the forms of energy crossing my boundary into my system, all the forms of energy leaving, crossing my boundary, all the mass entering my system, all the mass leaving my system. So I'll get to entropy in a second. Let's just do heat. Q in minus Q out. Now, first law equals delta U minus dW. Okay, so for entropy, I have S in minus S out plus S gen equals delta S of my system. Okay, so this is of the system. So if I know my system is a stainless steel wall, right, stainless steel cylinder, filled with air, that's my system, and I know the temperature of my air inside and the stainless steel, I can look up what the entropy is at a given state, right? I go look up in some stainless steel, in some alloy, right, handbook, it tells me the entropy of stainless steel at a given temperature and pressure, right? Per unit mass. So then I know the wall thickness, whatever it might be. I calculate the total mass of my stainless steel wall. I know its temperature and pressure. I calculate the total entropy, right, of my container wall. Then I have a gas. I know its volume. I can give you the density. I can just tell you the total mass inside. I give, you look up air, get the temperature at a given temperature and pressure. I can calculate the total entropy within, right? So then this is delta S of the system, so this is delta S between two states, right? State 2 and state 1. To go from state 2 to state 1, I had to add entropy. Really, I had to add energy and heat, right? In the form of heat, mass, and work. And I had to remove energy in the form of heat, mass, and work, which then are coupled to these. So to go to a different state, I have to bring in energy or bring out energy. Equivalently, I add entropy, I remove entropy. So this is the first law. If I want to do the second law, I have Q in minus Q out equals what? TDS. So if the net heat is in and there's no work done, what happens to my internal energy? So constant volume, addition of heat, what happens to my internal energy if there's net heat in? This is U2 minus U1, right? So add heat at constant volume, no boundary work, entropy increases, right? If I add heat, okay, I can say constant volume, all this other stuff, I can make all those other restrictions, right? But just looking at heat, net heat in, say I have a constant boundary temperature, what happens to my entropy? Okay, so there is a case where I could have some varying wall temperature of my system, right? But typically in thermodynamics, we want to simplify this temperature of the boundary. So let's just say any changes in temperature when I'm adding heat of my boundary are small. Then net heat in, entropy increases. If the net heat is out, net heat out, I decrease the entropy of my system. How do I get it net heat out? Right? that's an unnatural process, I have to do some work. So in this case, I might have to expand, right, my system. I add heat so if I have a balloon, say if I have a balloon, and I'm going to add heat to it, but I expand it, so the balloon inside this balloon is going to be gas, right? Say it's gas that we can say is an ideal gas, so we can use PV equals nRT. And I use a blow dryer to heat it up, but at the same time, I do work on it and I expand it, right? So by doing that, I'm adding heat, but I'm doing work. I'm expanding it, so I'm doing work to expand it. So typically that PV means balloon's doing work on the surroundings, but nevertheless, I expand it, so I can expand it more than what natural heat I added would expand the balloon. So if I did no work on it, right, and I just added heat to it, and I say the balloon expanded at constant pressure, this would still be, in this case, I'm adding heat, right? This would still be positive, right? I would still increase the entropy. But if I were to add heat and do work, expand it more than it would naturally expand, I could get S2 less than S1. But then this heat in, there'd be some boundary, then we'd have something coupled there with the work in. So end story, heat is coupled to changes in internal energy mass of system, well, not necessarily mass of system, but I guess mass of system, and work done, and entropy. So energy transfer to or from the system is by two mechanisms. I should say, I said energy, but I should say entropy. Heat and mass. Energy transfer to or from a system. 1 second, thank you. So here I have energy, not entropy. Energy transfer to or from a system. So entropy transfer to is S in, from is S out, right? Energy transfer to or from a system, energy in, energy out, is by three mechanisms. Heat, mass, and work. First law. Couples them. The entropy transfer is mainly the second law, but also the first law couples this heat and mass. So entropy transfer by heat, we can write it in an equation form. So the entropy transfer due to heat from going to state 1 to state 2 is delta Q over T. And I can, instead of writing it in integral form, I can write it in a summation form. Equals the sum So I took my integral and I wrote it in sum form. So let's just picture a balloon, since I've already talked about a balloon. And let's say on one half of the hemisphere of the balloon, I add heat. And in another half of the hemisphere, I remove heat. So let's make it pixelated even more. Let's say on one half, I add heat, and then on a quarter of the other half, or half of the half, I add heat, and then I remove heat, right? So here, this just identifies this all as an integral, and I'd have to put this in spherical coordinates, right? And do the integral. But I can, like what we do with a computer, is I would just break this up into 3 pieces. The heat added to one half of my balloon, right? The heat added to a quarter of my balloon, and the heat removed from a quarter of my balloon. So entropy transfer by mass, I can write in a similar expression. The total entropy added by mass is integral from 1 to 2 S dm. Okay. More related to what we would do, or what we have been doing when we do energy balance, is equal to sum K Sk Mk. So in this case, right, counterflow heat exchanger, I have water coming in, I have oil coming in, okay? So, and then I have water leaving, oil leaving, so my total entropy added to my system by mass is equal to, so if I break, it's the sum of all 4 parts. So the first part would be the entropy of the water coming in times, and I can put it in rate form, times the total mass that came in, right? So it came in at a given temperature and pressure. Then I'd have the oil, so I'd have the entropy of the oil at a given temperature and pressure times the mass of oil that entered my system. Then I'd take the other part, the entropy of the oil leaving at a given temperature and pressure times the total mass of oil. So when we've drawn these, when we've solved problems previously, we've always kind of broke it up into terms like this. I'm just pointing out that really it's this. It's an integral, but we can, when we solve it with a computer, we don't use MATLAB or MathWorks or all this other stuff, right? Or Mathematica. We typically break it into segments and pixelate the process. So entropy transfer by work is 0. So I can have some mass 1 in, I can have a mass 2 in, and I have my boundary of my system. And let's say that my boundary is at some temperature Tk. My surroundings are at some temperature and pressure. I can have heat in. So I have mass coming in, mass coming, 2 forms of mass coming in. There's no mass leaving. I have heat coming in. I have to know the temperature and pressure of this mass coming in. Right? Once I know the temperature and pressure of the mass coming in, I can get my entropy per unit mass. Likewise, if I know the temperature and pressure of my second form, so maybe this is water and this is oil. The oil's coming in at a given temperature and pressure, so I know the entropy per unit mass. Where both of these are big S2, right? So the total entropy coming in is related to the mass times its entropy, right? This part plus that part. Now this is just, so big S2 and big S1, which I didn't write out, is entropy coming into my system by mass. I also need to know the entropy coming into my system by heat. So I've already defined my boundary temperature as T sub K. So my S in, I'm going to put mass here, heat is equal to Qn over Tk. And likewise, S total mass is equal to S1 mass plus S2 mass, and S total in heat is just this, because I only have one form of heat coming in. Any questions? So let's talk about entropy generation a little bit more. So I have S in minus S out plus S gen equals delta S system. Remember, S has units of energy, right? Joules per Kelvin. In the back of the book, small s is typically written as kilojoules per kilogram per Kelvin. So this is entropy per unit mass, this is big S. So heat and mass, generation, change in system entropy from going from one state to another state. This on this side is always the change in entropy from one state, equilibrium state, to another equilibrium state. S2 minus S1. Okay, I can do this in rate form. Sn dot minus S out dot plus S gen dot equals delta S dot system. So the units of this are kilowatts per Kelvin, right? Joule per second is a watt. So the rate of entropy added minus the rate of entropy removed. Then I have this S gen term. This has to be greater than or equal to 0. And S gen has to be greater than or equal to 0. So let's do a closed system example. So closed system, no mass transfer. So I have S in minus S out plus S gen equals delta S system. So let's say that this is my temperature of my surroundings, and I have some heat out, and I have some boundary temperature. So closed system, no mass transfer, only heat transfer. So S in minus S out is by heat only. So I can rewrite this as an integral, right, of delta Q over T plus S gen equals delta S. Now in this type of drawing, there's only heat leaving, right? So this ends up, so I can if this is just, this is the total amount, right, of heat. This is the differential amount of heat. So I can rewrite this in a simpler form and just write it as big Q over T. But that meant that temperature didn't change when I was at each incremental step of heat removal. let's consider an adiabatic. Closed system. So if it's an adiabatic closed system, I have no mass or heat. I should say no net heat. So adiabatic closed system, it's no net heat. Isolated system, no mass or heat. So no net heat transfer. So when I do this S in minus S out, right? We already know that this integral is 0. So another way to write it is so my S in minus S out is equal to 0, my net heat transfer, and then that gives me S gen is equal to delta S. So if I say its total heat is equal to 0, then we know that S gen has to be greater than or equal to 0. So if I go to two different states, this would be a natural process. S gen has to be greater than or equal to 0. So S gen has to be greater than or equal to 0. So if I'm not adding any heat, I'm not adding any mass, and it goes from one state to the next, that has to be a natural process, right? And then this breaks down to what we already know from the second law. So let's do adiabatic. Of a closed system of components. Plus surroundings. So no mass transfer. So it's of components, so we'll say component A and component B. And I have my surroundings. So adiabatic entropy balance of a closed system. So adiabatic means delta Q. There's no, so I can have Q in, right? But it has to be balanced by Q out. So there's no mass transfer across my boundary. So here I have closed system. So there's no mass that crosses this boundary. And within that I have surroundings. Of course, outside I have more surroundings. But here I have a multi-component system. So say this is your computer, this is you, this is the room you're in. You can have interaction, there can be mass transfer, so you spit on your computer, whatever you want to, however you want to look at it, right? So within here, you can have mass transfer. There can be mass transfer between your surroundings and your system A. You can have mass transfer from B, but there's no mass transfer between your multi-component system and outside the boundary. Likewise, I can have heat transfer like this So I can have heat transfer within, mass transfer within. So in this case, I have S in minus S out plus S gen equals delta S. So it's adiabatic, right? So I know already, the same as before, that if I integrate all over all the heat in and something, this boundary temperature here, right? And I Q in over TB plus this Q in over TB minus Q out, we already know that this is equal to 0. So the heat form is, so, and there's no mass transfer across the boundary, so I know that both of these are going to be equal to 0. Which then gives me S gen equals delta S. So I have S gen equals delta S. Well, now I have a system, right? So this delta S system equals delta SA plus delta SB plus delta S surroundings. So my system is a multi-component thing. It's the room, it's the computer, it's me. There's no heat or mass that's coming in and out of the room, right? But I can have heat or mass transfer within. Well, I drew my boundary like this, so when I do entropy balance, I'm not concerned. I'm not solving for this. All I'm looking at is the change in entropy of my system total relative, and that's equal to the sum of each individual component within my boundary. Well, I should say minus QL. So the total amount of heat transfer across to my surroundings is equal to Q in minus Q out. We know because it's adiabatic that delta QS equals 0. So we know that Q in net is equal in magnitude to Q out net. So let's draw a little bit different. This is a little bit different, and let's go back to kind of a control volume perspective. So now I have a control volume. Of course, here I also have a control volume. Right? There's a control volume associated with it. But we'll look at it like this. So I have mass 1 in, mass 2 in, mass 3 out. Of course, given this mass is coming in and out, this can still be of a multi-component system, but let's just do this. So this one has a temperature, right, and a pressure associated with it. And given that I know that, I know U3, I know S3, I know H3, right? So if I tell you the mass, the temperature, pressure of the mass leaving my control volume, then I can go look up in a table the entropy per unit mass, the energy per unit mass, the entropy per unit mass, and the enthalpy per unit mass. Likewise, I can do the same thing here. So let's do the control volume, where I have Q1 and Q2. So if I do full entropy balance, I have the sum of QK, TK, right? Plus the sum MJ, SJ, plus S gen equals delta S, my control volume. So I just changed the term from system to control volume, but the same applies. And I can break this up into heat in and heat out. right? So Q in is going to, or I can leave it like that, where I just have a sign convention where Q out is negative. So when I do all this stuff, I have to define a boundary temperature. Say I have this is my boundary temperature there, and that is my boundary temperature here. So this equation breaks down to Q1 over T1, Q2 over T2, plus M1 S1 plus M2 S2 minus M3 S3 plus Sgen equals delta S my control point. So I just added in minus out, plus Sgen equals delta S my control point. So there's such thing as what they call TDS relationships. And it turns out that there's a first and second TDS relationship. So what I'll do is I'm going to first derive the first TDS or Gibbs equation. So anybody in here in chemistry? One person? So the Gibbs equation is used a lot in chemistry. So thermodynamics, first TDS, chemistry perspective, Gibbs equation. So to derive the first TDS expression, let's start with the first law. And I have delta Q internally reversible equals du minus some incremental amount of work. So this is work done on or by. This is work done on the system, right? So it's the same. So if I could put a plus sign here, but then I'd have to say it's work by. So this is work done on the system. So I'm going to put on, internally reversible. Okay. This is of a closed, stationary, internally reversible, fixed mass, and compressible system. So compressible, I can compress it, so I can say gas, right? Stationary, we're not talking about my system, say, moving at speeds relative to the speed of light, something close. So you could say stationary, but there's no real inertia that we have to include in the thermodynamics. It's reversible. Fixed mass, we're not adding mass to it. So we can just consider it a balloon, right, filled with gas. So when I have this here, and I already know that the incremental amount of heat can be expressed as this from the second law. And I know that delta work on is equal to minus P dV. So just as a note, I can do this. Okay. But this is work by. And delta work by is equal to P plus sign, minus sign. So I combine the second law with the first law. I have T ds is equal to du plus P dV. And this here, this expression, is the first T ds relation. So I could say I could use the terminology of work by the system, and if I still have delta Q is equal to T ds, so I replace this into here, I still end up getting the same thing, T ds. Now I have the plus sign, du plus P dV. So it doesn't matter whether I choose work on or work by to derive the first, I just have to make sure my sign convention sticks with that. So we have the first TDS relationship. So the second TDS relation, what we do is we look at the relationship between the enthalpy and the internal energy, okay? And now I have dH is equal to du plus P dV plus V dP. So this here is just, chain rule form, right? I can rewrite dH, I can rewrite this in terms of du. So du equals dH minus P dV minus V dP. So I have this expression, I have my first TDS relationship. So using this expression and my first TDS relationship, I have TDS is equal to dH minus P dV minus V dP plus P dV. So my P dV's cancel, and I have T ds is equal to dH minus V dP second T ds. Okay, so just looking at these by inspection, when would it be useful to use the first TDS relationship? Think about different processes, right? We had isobaric, isothermal, adiabatic, isentropic, right? Polyotropic. There's all these different processes to go from one state to the next. So what type of process, if my system was undergoing, what type of process would I want to use the first TDS relationship?
Constant volume.
Yeah, constant volume, right? Use it. I already know that the change in entropy is related to the change in internal energy, given that I know a boundary temperature. When would the second TDS relationship be useful? Isobaric, constant pressure. So if I have a constant pressure process and I want to calculate as gen, I know that I can relate the change in entropy of my system related to the change in enthalpy of my system. If I have a constant volume process, right, I can relate the change in entropy of my system to the change in energy in my system, internal energy in my system. So these are just two different relationships. They start from the first and second law. Second TDS, I use the correlation between the enthalpy and the internal energy. So let's write these out in a slightly different form that is used for gases quite commonly. So I have the first TDS relation, or Gibbs, and the second TDS relation, I like enthalpy. So I usually say enthalpy so I know that H is equal to U plus PV, but so the first TDS relation, I have T ds equals du plus P dV. And the second TDS relationship, I have T ds equals dH minus V dP. So I can redo this, and I can put it, I can divide by, so ds is equal to du over T plus P dV over T. Likewise, ds is equal to dH over T minus V dP over T. Now these are big S's, so I can do the same thing and make it small s's. D small s equals d small u over T plus P d small v over T, and likewise ds is equal to d small h over T minus small v dP over T. So let's write this in integral form, because this is a differential, the differential change in entropy. This differential change in entropy, differential change in internal energy, right? One's per unit mass and the other isn't. So let's go to delta small s is equal to what? Just from here. Delta small s is equal to what?
Just S2 minus S1.
Okay, I can do that. I can write S2 minus S1. Let's do that above. It's not quite what I'm getting to. Okay, let's think of it more in terms of calculus. In terms of calculus, what do I write?
The integral from 1 to 2.
Mm-hmm. Right. So if I integrate this from 1 to 2, I end up getting S2 minus S1, right? So all I want to do is to get you guys to, so I can do the same thing, right? Delta big S equals the integral from 1 to 2 d big U over T plus the integral from 1 to 2 P big V over T. So if the temperature is constant and I know the pressure, how that goes as a function of volume, I can calculate this integral easily, right? Likewise, if temperature is constant, or U might be a function of temperature, which we know the specific heat at constant volume, there's a relationship between du and temperature. So same thing I can do here. Delta S is equal to the integral from 1 to 2 dH over T minus the integral from 1 to 2 V dP over T, or big S is equal to the integral from 1 to 2 dH over T minus the integral from 1 to 2 V dP over T. So both of these are basically just, we can get change in entropy by integration. So let's just recall that delta U is equal to CV times M dt, and d small u is equal to CV dt. Likewise, dH, Cp dt, or by the other definition, CV equals the partial of U with respect to T, right, at constant volume, and CP equals the partial of H with respect to temperature at constant pressure. So here I just integrate both sides. I end up getting a delta U, right, integrate both sides by change in temperature. So we go from this to these. Okay, so given that we know this, we have expressions for the internal energy as a function of temperature, and we have expressions for the change in enthalpy as a function of temperature. So let's look at the entropy change. For liquids and gases. So just as a side note, typically liquids and some solids are incompressible. So related to this, the specific volumes are almost always constant. For a given temperature change. So specific volume, that's my small v, okay? So my d small v is equal to V2 at T2 minus V1 at T1, which is approximately equal to 0. So delta S small s is equal to the integral from 1 to 2 du over T plus integral from 1 to 2 P dV over T. And I can use CV relationship, so I have the integral from 1 to 2 CV dt over T. Which equals approximately the integral from 1 to 2 CP dt over T. CV equals approximately CP for solids and liquids. So let's just look at this piece here.
Is that average?
Yeah. So I can, so we already talked about how CV is pretty, so if this is a small, Now this doesn't apply if I have a phase change, right? So if from state 1 to state 2, if this is liquid and this is gas, I can't do this. I have to break it up into a separate part, from going from liquid at one temperature to liquid just before phase transformation, have this, then I can use this average, but it's not T2, it's some other, it might be T2, right? But then I have to get the part of the gas. But if I remain constant phase for a liquid, gas, and solid, this works. Well, not always for a gas, but definitely for a liquid and solid. So let's look at an isentropic process. On an incompressible So isentropic process, incompressible. So incompressible, delta S, delta V, and in addition to this, delta Q is equal to 0, right? So I have delta S equals CV average, natural log T2 over T1, which equals what? 0, which implies that the natural log of T2 over T1 equals 0, which implies T2 equals T1. Let's do an ideal gas. So an ideal gas, I have the ideal gas law. Right, I can write it in both forms. So let's write out the first TDS. Let's do also the second TDS side by side. And for an ideal gas, right, I have a relationship for the pressure as a function of specific volume. And also for an ideal gas, I can use the standard relationship for the heat capacity at constant volume. So I have dS is equal to CV dt over T plus, and then here I descended V dV over, excuse me, my T's cross out. Likewise, I have here dH, Cp, dt over T minus, now I can write V as a function of P, so I get R gas T over P, T, dP, those cancel out. So when I do this integral, I can write it as an the total change, or my delta S is the integral from 1 to 2 CV dt over t plus our gas, the integral from 1 to 2 dV over V. Same thing, S2 minus S1 is equal to the integral Cp dt over t from 1 to 2 minus our gas integral from 1 to 2 dP over P. Now I know that this is equal to just the natural log of V2 over V1. This is equal to the natural log of P2 over P1. This we've already solved for, so I can just write delta S equals approximately CV average natural log T2 over T1 plus R gas natural log V2 over V1. Delta S equals CP average natural log T2 over T1 minus R gas natural log T2 over V1. Okay. Same end story. We looked at the delta S. This is for the first TDS relationship, whether it's a gas, useful constant volume process. Second TDS, useful for a gas, constant pressure process. So when we do analysis on the system, this is delta S of our system. All we need to know is the average heat capacity and the initial and final temperature.